Okay, hi everybody. So we have this sequence here, and we need to prove that it converges. Okay, using the convergence game just means using the full definition of what it means for a sequence to converge. So first, it's helpful to give names to things. So let z to the n be 3 plus 2i plus this thing to the n for every n. So now we've defined a sequence. Okay, and also, of course, a sequence is a map from the natural numbers to some number system. Okay, and now to figure out what does this converge to, let w equal, so w will be my name for the limit that it converges to this number. And what number will it converge to? Well, turns out it'll converge to this piece. Why? Because this piece will just sort of go to 0. As n goes bigger and bigger and bigger, this will go to 0. Why? So let's see. Where is this number? Here's the complex plane, 0.8 and then 0.5. That's maybe here. Now, it's not super clear, but it turns out that this number is inside of the unit circle. Let's check that. What is the size of this number? Let's call it, maybe it's called C. Or let's just calculate what's the size of this number. Well, the size, well, what do? I just take square root of 0.8 squared plus 0.5 squared. That's the definition of the norm or modulus or size or absolute value. It's Pythagorean theorem, really. So 0.64 . Okay, so this is some number, and you'll notice it is less than 1. And so it really is in the unit circle. What's going to happen is we're going to keep, it has some angle, and we're just going to keep marching around by that angle. But we're going to keep shrinking because each time we multiply by the size of that number, as we multiply, and so it's going to sort of spiral around and get smaller and smaller and smaller and go to 0. So this piece will go to 0, and this will be the limit. Now, how to prove it? Okay, so theorem. Z to the n converges to w. Another way to write this is the limit of the z sub n is equal to w. I don't really like this one as much. For whatever reason, I like this notation. Okay, proof. So first, we have to remind the reader. So now our reader has to try to understand what we're saying. That is difficult. It's difficult to read somebody's math. So let's make it easy for our reader. Remind them what this means. Remember that z to the n arrow w means that for all d, there exists a capital N natural number such that when you go past that cutoff, then the z sub n and the w, the distance between them is as small as you like. Okay? There's an implies. You do slash implies to get this thing in LaTeX. Such that this should be a natural number, and this is a positive number. It's a distance. It's like the size of a little ball. Wherever Zn is and wherever W is, they should be inside a ball of radius d. Okay. So, how do we prove this? Well, no matter what d is chosen, because it's for all d, no matter what d is chosen, we need to be able to find. Okay. So how are we going to do this? Well, we have no idea until we start looking at this thing. This is our goal. And so we should calculate with this, just start to try to understand it better. Otherwise, we have no idea how to prove. Okay, so let's calculate. Z to the n minus w less than d. That's if and only if. And now I'm just going to use the definition of z to the n, which is over here, and w. There's z to the n, and now I need to subtract what? I need to subtract w. Okay, well that is nice, because these just go away. Okay, so then this is true if and only if this is true. You have to raise it to the n and then take the absolute value, less than d. Okay, but for any complex number, z to the n is equal to the absolute value of z to the n, because when you repeatedly multiply by a number, the magnitudes just multiply. In other words, like z times z is z times z, etc. So we can go like this, to the n. Sort of like you're going to take this and then we're going to raise it to the n, less than d. And that is if and only if. Oh, but we actually calculated this. This was square root of 0.89. In other words, well, obviously, well, not obviously, but you have to remember that the size of a complex number is a real number. Even if z is complex, the size of z is a real number. In fact, it is non-negative. It's either positive or it's 0 if z was the 0, the origin. So that's awesome. I forgot the to the n. That doesn't just disappear. I just knew that the norm was square root of that, and so now we have to raise this to the n. Okay, so let's actually give this a name. Now, let c be equal to the positive number like that. Then we have c to the n less than d. Now look at this. This is strictly less than 1. By a previous problem, we proved that c to the n will go to 0. We proved this if c is between 0 and 1. Oops, 0 and 1, which it is in this case. But what does c to the n arrow 0 mean? This means that for all d, there exists, we can say that there does exist an n. And let's even just say it very nicely. Thus, there does exist some capital N, such that going past that capital N implies c to the n is less than d. And I mean, I guess we could do c to the n minus 0 just to be very careful, which is true if remember c is positive. It's square root of 0.89. It's a very specific number, actually, c now. But this would work for any positive number that's less than 1. So we can just get rid of the absolute value sign because it's positive and just say c to the n less than d. But look at that. That means that the same n will work because this, now, okay, let's call this. So let's give these calculations a name, star. If and only if, by the calculation star, we can go from here all the way up to here, z to the n minus w less than d. And so we are done. So we proved that z to the n, this sequence, limits to w or converges to w. And that is the end of the proof. And Yeah, I guess I would even just, based on the way I explained it, I would just keep it in this order. Yeah. Okay. Can you prove this yourself? Take this blank sheet of paper and try to prove this without looking. Okay, and really try to think of it like in your own words, your own story of why this is true.